Reviewing from last time, if I have two vectors A and B, where A has components AX in the X direction and AY in the Y direction, and B has components BX in the X direction and BY in the Y component, in the Y direction, and I want to add those two vectors together, all I simply have to do is add the components for each direction. So I would say the sum of A and B has a component AX plus BX in the X direction, and AY plus BY in the Y direction. Now we're going to talk about motion. So consider an object. T0 has a position Ri for R initial, and a final position Rf over here after 1 second. So we have our motion diagram taking us from time 0 to time 1, and from initial position Ri to final position Rf. Well, previously, when we were dealing with motion, we looked at the displacement of an object, which we said in one dimension we call the delta x, and that was just equal to x final minus x initial. Now we can do the same thing. We can define a change in position. I will represent by that green arrow, which we will call delta r. And just as before, the change in a vector's position is going to be the final vector minus the initial vector, which we may write as delta r equals r final minus r initial. Now we have not talked about subtracting vectors, but much like addition of regular scalar numbers, subtracting a vector is the same as adding the negative of that vector. And we know how to add vectors, so we can subtract vectors just as well. All you're going to do is subtract the Ri components from Rf. So you'll have the x component of Rf minus the x component of Ri, same thing for the y component. But this will give us the change in position from R initial to R final. Similarly, we described the velocity or speed of an object. We really did speed, because we haven't dealt with multidimensional vectors yet, as delta x over delta t. So the change in the position over the change in the time, or the displacement over the change in time equivalent. So we can do the exact same thing to define our vector velocity. It gets the same symbol, but all we do is put the arrow on the head on top of it to make sure we're calling it a vector and not a scalar. But that is just going to be delta r divided by delta t. So just like when we're adding vectors, all I'm doing is I'm going to divide each component by that delta t, by that scalar. Let's take an example of how to compute velocity with vectors rather than scalars. Well, we start here with 2 points at time 0. I am over -3 and up 2. So my vector position, my r initial, is -3 in the x direction and 2 meters in the y direction. And then I end up at this point here, which is over 3 and up 0. So my vector position would be 3 meters in the x direction and 0 meters in the y direction. All we're going to do is use our formulas to compute the vector displacement and the vector velocity, also known as just displacement and velocity, since those are defined to be vectors. So let me compute my displacement first. I'm going to take delta r is r final minus r initial which if I just look at my vectors here, what I'm going to do is take r final minus r initial for each component. So for the x components, that would be 3 minus -3. And for the y component, that would be 0 minus 2. And those are both in meters. Doing out the math for that, I would have 3 minus -3. So that would give me 6. And then 0 minus 2 would give me -2. So my displacement would be over 6 meters, over 6 meters to the right and down 2 meters, which is exactly what we have here. If I draw my delta r from initial to final, we can see that I've gone over 1, 2, 3, 4, 5, 6 spots to the right in the x direction. So positive 6 in the x direction. And down 1, 2 spots in the y direction. So I've got -2 for my displacement in the y direction. The next thing we want to do is compute the velocity, which to get the velocity, all we have to do is take delta r over delta t. So to do that, all I'm going to do is say that my velocity equals, let's see, that would be delta r vector over delta t, which will be 6 divided by 1, and then -2 divided by 1 meters. So in this case, my velocity would have the same numbers as my displacement, just because I'm dividing by 1 second. Now, if I were to, let's say I would have a different time, say this for 2 seconds, I would be dividing by 2 here. So my velocity would be 3 meters per second in the x direction, -1 meter per second in the y direction. So there's an important take-home point here. I get velocities that are different in different directions. So we have an x velocity and we have a y velocity here. We can actually write that out more explicitly. I have this x velocity, which in this case is 6, positive 6 meters per second in the x direction. Actually, I messed up here. This should have been meters per second, since I divided by seconds. And I have a y velocity, which is going to be -2 meters per second. But my x and y velocities are completely independent of each other. I have a velocity in the x direction that doesn't at all affect the velocity in the y direction. This is a point we're going to be exploring a bit more as we talk about motion. One more important point that I should mention about motion. So far we have been talking about motion with a constant velocity. What I mean is objects that are moving at a constant speed, moving in the same direction all the time. If I do that, if I make the restriction that the motion has to be at constant velocity, then I can write that my velocity is just the change in r over the change in time, because it's never changing. However, if we're talking about motion with acceleration, I have to write this as the average velocity, because my delta r over delta time, that could be changing. All I'm looking at is 2 points and computing r final minus r initial to get my delta r. I have no idea what happens in the middle. So my velocity, maybe I'm going up, this is my motion diagram, maybe I'm heading up this way at one point, but then heading this way and then heading down. But if I only look at the points at the end, all I'm going to get is the average velocity between those 2 points when I compute the displacement between those 2 points. if you want to compute the instantaneous velocity, which is how fast you are moving at any particular point on that motion diagram, then what you have to do is make this delta t very, very, very small. So if I only look at points that are very, very close to each other, I don't take points that are far apart. I take these 2 points that are right next to each other there, then you will get the instantaneous velocity. And we write that a different way. We write that in calculus speak using a derivative. Most of you will not go on to take the calculus version of this class, but if you do, just know that there is a difference between the average velocity and the instantaneous velocity. Where instantaneous velocity, we have to use the derivative from calculus to compute how fast or what your velocity is instantaneously. For the most part, we're going to stick with average velocities for the algebra course. We've talked about motion at constant velocity. Now we're going to talk about motion with acceleration. Now, recall from last semester that acceleration was just the change in the velocity divided by the change in the time. It's going to be the same thing here, now that we're dealing with multiple dimensions, except now we have to deal with vector velocities and vector accelerations. Let's say you're moving in a circle. Let's say you're moving in a circle at constant speed. You're just going around at the same rate all the time. Well, we can make a motion diagram. We can put different points on the circle, saying where you are at any given time. And we can also draw velocity vectors on that circle. So we can say, let's say that here is where you are at t initial. Well, you're moving up and to the right because your next point is going to be over here. So I'm going to draw my velocity vector up and to the right. Now there's an important point about velocity vectors when you're dealing with multiple dimensions and you're moving along curved paths. And it's that the velocity vector is the tangent line to the curve that you are tracing out. So when I draw my velocity vector here, I'm going to call this v initial. That velocity vector is going to be tangent to the circle. That tells me its direction. Its length I'm going to make proportional to its speed. So this vector has a length that would be larger if the object were moving in a circle faster, and it would be a smaller arrow if the object were moving slower. But here's where we are initially. Let's wait a second and see where we are. Now let's say, 1 second later, we're over here. How do we draw the velocity vector at that point? Well, again, it's going to be just a tangent line to that circle. And if we're moving at a constant speed, these arrows have to be the same length, which they are more or less. We would say that maybe this is our final velocity. So this is the average velocity, or sorry, excuse me, this is the initial velocity at this point, and our final velocity occurs at that point. So on average, we would expect to get a velocity that's something between these two. But we're actually not interested in the average velocity. We're interested in the change in velocity, which is going to be written as delta v. We're interested in that because we want to find the acceleration. So let's look at the change in velocity for those 2 points. I'm going to write our initial velocity this way. Okay, all I'm doing is I'm moving these arrows over here, so I have a new clean diagram to work with. And I'm going to connect them, their 2 ends together. So I can say one velocity vector points up and to the right, one points down and to the left. What's the difference between those 2 velocity vectors? Well, the difference is this one points here, this one points here. So the difference is down like this. That would be delta v, It's just the vector pointing from the head of the initial arrow to the head of the final arrow. And that's going to tell me the direction of the velocity. Or excuse me, the direction of the change in the velocity, which, since the acceleration is going to be written as, the vector acceleration now, is going to be written as the change in the vector velocity divided by the change in the time. We're going to treat this as a definition, so I'll give it 3 equal signs. The direction of my acceleration has to be pointing down based on the change in the velocity. Well, if I look between these 2 points, the top of this circle is right between those 2 points. This is going to give me my acceleration, really my average acceleration, so I'll put an average down here, between these 2 points, which means between these 2 points my acceleration is going to be pointing down. And this will generally be true for circular motion, or for any curved motion for that matter, is that your acceleration points into the curve. So whenever you are changing directions, if you are running, or you're driving a car, or you're moving in any way, and you're running and moving along a curved path, you're accelerating in the direction that you're curving. So here, the circle always curves in, so the acceleration is always pointing in. To reiterate, the acceleration is defined as the change in the vector velocity divided by the change in time. And in general, if you are changing the direction in which you are moving, you are going to have some component of the acceleration that points into the curve. Now there's a special case of that when you are moving at constant speed. Now remember that speed is not the same thing as velocity. Speed gives you the same units, so you're still getting meters per second. It tells you how fast you're going. But unlike velocity, speed does not have a direction. Velocity, in order to specify velocity correctly, you have to specify what direction you're moving. So to get some practice with that, let's say we're moving along this curve at a constant speed, and you want to draw your velocity vectors. Well, we can draw our velocity vectors as being tangent to the curve. So tangent just means it runs, the vectors run parallel to the curve at any point. So at this point, the velocity vector is pointing along the curve, same thing here, same thing there. And all of these points, my arrows are along the tangent line to the curve. And we can write our acceleration too. Now, notice that I've drawn all of these arrows about the same size because I said we're moving at a constant speed. But even though we're moving at a constant speed, the velocity is still changing because we're changing direction. If the velocity is changing, whenever I have a change in velocity, even if the speed is constant, if I have a change in the velocity, just by changing the direction, you still have acceleration. And you accelerate into the curve. So here, I was going up and to the right. Now I'm just going up. So the net change is going to be going down. And again, that's going to be into the curve. Same thing at this point, into the curve, into the curve. These are all acceleration vectors. I can do the same thing over here, into the curve, into the curve, into the curve again. These purple lines are acceleration, the green was your velocity. What about at these points? Well, at these points, here, there's not really much curvature here. It's about going straight and then it starts to curve up. So here, we're concave down, or the technical term for that is frowny face. Frowny face over here, smiley face on that part of the curve. So the curvature is actually changing here. And that's an important point. Here my arrows are pointing in and down. Here they're pointing up. In the middle here, it turns out there's not much acceleration because we're not really changing direction. Here the arrows were pointing more down. Over here they're starting to point more up, again because the curvature is changing. Here it's not really, at this one point, it's not really changing very much. So we would say at this point our acceleration was going to be 0. Now, the fact that you get acceleration when you have curvature leads us to believe that acceleration is somehow related to curvature. So if you're curving a lot more, it means you're changing the direction of your velocity even faster, which means you have to have a higher acceleration.